So, but the binomial series, totally different, kind of. So it's a way of writing out 1 plus something to the kth power. And oh my gosh, I believe it is, yeah, that sounds right. It's 1 plus k times x plus k times k minus 1. This one's one that's always impossible to remember. Let's take a look here real quick. Oh, wow, I pressed the button. Oh my God. It's a real fun day for technology here. I want to see binomial series. So I want to make sure I'm not blowing it here. Oh yeah, there we go. K times k minus 1 over 2 factorial times x squared. And then you just keep going in the same sort of way. The next term is you just subtract the next thing. So k times k minus 1 times k minus 2 over 3 factorial times x cubed. And the next one would be k times k minus 1 times k minus 2 times k minus 3 over 4 factorial times x to the fourth, and so on and so on and so on and so on. And the way you write it out, so the thing is, it's really hard to write out using a sigma unless you've talked about the thing we just talked about. So you can definitely write this as the sum from n equals 0 to infinity of k choose n times x to the n. If k is a positive integer. The formula is not true if k is not a positive integer, right? This choose function here only works if k is bigger than n and it's an integer. There's no like choose function for like 57.2 choose 3. Like you can't do that. Or at least not, at least I should say, I don't know of a way that that's done. Not say you can't do it. I just don't know about it if it's possible. Um, Question.
Wait, can you go back to the other?
Sure.
If if we can you use this n factorial over n minus k factorial times k factorial? Can you use that to simplify?
If
If
k is an integer, positive integer. So right here, right, this here, that part looks like k choose 1. That part looks like k choose 2. That part looks like k choose 3. But again, only if k is an integer. And the thing here is that you don't actually use this series if k is a positive integer. Because you can multiply out 1 plus x to the 7th power. You don't need a power series for that. So although you could use this if k is an integer, we really don't. Like this is more useful, for example, like say, find the power series, Taylor series, whatever you want to call it, for the square root of 1 minus x cubed. So then what you do is you say, okay, well, I'm going to think of this as it's really 1 plus negative x cubed to the 1/2 power. So then in this formula here, x is getting replaced by negative x cubed. I should have put in the cube. Nah, I don't love my choice for parentheses there. Sorry. That's a better choice there. Um, and I don't love that either. The 3 should really be on the x there, but it doesn't actually make a difference, but I don't like it. And so x is negative x cubed and k is 1/2. So if I start writing this out, it's going to be 1 plus my k is 1/2. So it's 1/2 times negative x cubed. And then it's 1/2 times 1/2 minus 1 divided by 2 factorial times negative x cubed squared. And then it gets super gross really fast. 1/2 times 1/2 minus 1 times 1/2 minus 2 over 3 factorial times negative x cubed cubed, and so on and so on and so on. So in my opinion, that's what the binomial series formula is for. Is for when you're trying to do something like this. And again, you don't want to do it the long, tedious way, where you find a bunch of derivatives and then plug in your center and then find you find your sum from n equals 0 to infinity of your nth derivative at your center over n factorial times x minus your center to the nth power. That's a much, much more awful way of doing this kind of problem. Just like you don't want to find the formula for sine of x, you just want to memorize the formula for sine of x. Same kind of idea here.
Is there, what's that? What is for how can I just resolve solve it?
Solve what?
The
Sure. Well, maybe. I'm not so great with power series, so I can try my best. What's the question?
system of n equals 1 to infinity of 1 over n times 7 to
N times 7 to the n. Cool. So, any guesses as to what test might be the most useful test to use here?
Wait, there's no.
negative. It was -1 to n times the whole thing.
Like that?
N plus 1.
That? Cool.
Is this?
We've definitely talked about stuff like it's been a minute since we've talked about this, right? We've kind of moved on to vectors and cross products and stuff like that, but I'm happy to talk about this. It's still part of the content of this course.
I was just gonna ask. There.
No, so if it's a power series, if there's like an x to the n, this is just a regular, good old regular series. It's not a function. I don't see. I mean, you didn't say anything about x to the n. Is there an x to the n?
The n that was times 7 is an x.
So like 7 to the x,
No.
x right there. So typically, if it's a series you're trying to find the interval of convergence for, you would have like x. You would not have x in the denominator. You'd have like x to the nth power or x to the 2m power or something like that. I know for this, what's that? Okay. So this is just a straight
Oh.
convergence divergence question, I think. Unless they asked about conditional convergence.
It was this big.
Okay. So if I was answering this question, I would be asking, does this series converge absolutely, converge conditionally, or diverge? Looking at the fact that I have something to the nth power, I'm going to throw the ratio test at it. That was my first intuition there. Yeah. I don't want to do the alternating series test first ever if the question is absolute, conditional, or diverge. Because if you do the alternating series test first and you conclude that it converges, you don't know if it's conditional convergence or absolute convergence. Because if it absolutely converges, you have to do something else to show that. And if it doesn't, then you can say it conditionally converges.
So then you just take the absolute value and then.
Right. But here's the thing. Right. And the thing is with the ratio test, you don't even need to use the absolute value because the absolute values are already included. In fact, the ratio test, when you use the ratio test and you conclude convergence, you are concluding absolute convergence. So both the ratio test and the root test, when you're using them, if your conclusion is convergence, your conclusion is actually absolute convergence. So ratio test. So we're going to take the limit as n goes to infinity of the absolute value of an plus 1 over an, which is going to be the limit as n goes to infinity of, you don't really need to write the -1 to the n part, but we will here just for a moment. So it's going to be -1 to the n plus 1 over n plus 1 times 7 to the n plus 1 times the reciprocal of that, which is n times 7 to the n over -1 to the n plus 1. But as far as we're concerned, whatever -1 to the n plus 1 divided by -1 to the n plus or 2 divided by that is going to be a -1 or a +1, and the absolute value is going to be +1. So this part's kind of meaningless. So we're going to rewrite this as the limit as n goes to infinity of combine or group the like parts together. So 7 to the n over 7 to the n plus 1 and n over n plus 1. This part reduces to 1/7. So we have the limit as n goes to infinity of 1/7 times the absolute value of n over n plus 1. And what's the limit of n over n plus 1 as n goes to infinity? It is 1. So here our limit is 1/7, which is less than 1. So we get to say this series from n equals 1 to infinity of -1 to the n plus 1 over n times 7 to the n converges absolutely. That's kind of boring. Yeah, that's not fun either. Trying to think of a way to change this question to make it a little bit more interesting, but I don't have a good idea really. Does that seem clear as to what's going on? Cool, good. All right. Other trips down memory lane back towards series and stuff. Or shall we continue talking about three-dimensional interestingness? Yeah, let's go on. Let's see. Where were we last time? Oh, yeah, we were there last time. So, a reminder of a couple things. Last time, previously on, we talked about the cross product a bit. Specifically, we talked about how the area of a parallelogram can be found using the cross product. If you write your parallelogram like this, where you have vectors like here and here, and really like here's your parallelogram. If you call this vector v and this vector u and this angle theta, it is true that the area of this parallelogram is equal to the magnitude of u cross v. Or v cross u. It doesn't matter in this case, even though u cross v and v cross u are opposites of each other. If you take the magnitude, the length of the vector will be the same whether it's pointing, up or down. I don't think this is particularly interesting, to be honest, but the next part is, I think. So you can also use an extension of this to find the volume of a parallelepiped, also like a three-dimensional box shape, but you can also like tilt the box. Yeah. Parallelepiped. Here's how we'll spell it too. I pronounce it maybe incorrectly as parallelepiped. So here's what it is. The volume of a parallelepiped. Parallelepiped? I don't know. I feel like someone I once upon a time said it to me and it was parallelepiped. I don't know because things are parallel, but it's like got 3 dimensions. So,
Like a parallel.
right, it's a prism. It's a 3-dimensional prism. But there's lots of 3-dimensional prisms that don't have this particular shape. So we're trying to kind of specify this one. So any kind of like 3-dimensional rectangle you have is a parallelepiped. So is this. It's the thing I haven't drawn yet. It's just been tilted. So it's kind of like you have yeah. So here's my base. Which you could think of as being rectangular or parallelogrammy. And then it's going to have some height as well. Pardon me while I try to draw this. And the whole point is that the sides are supposed to be parallel. But it's called a parallelepiped, as far as I know. All right, here's my shape. I'm still going to have the same. For some reason, I've called these different things here. We're going to call this one u this time because, sorry. So we're going to call this vector u. We're going to call this vector v. We're going to call this vector w. And I'm going to point out that we already know how to find the area of the base, right? It's just the area of the parallelogram. And then all we have to do is have to multiply that by the height of this parallelepiped, so again, we've got sort of an angle going on here. So we need to know that angle theta right there to help us out. So let's do it. the volume is going to equal the area of the base times the height. Okay, we know the area of the base already. It's the magnitude of the cross product of u and v. So it's the magnitude of u cross v multiplied by the height. Well, the height is, sorry, I've kind of labeled this poorly here. Apologies. Let me scratch that. Let's call the vector w here. Let's say here's my height. And if I want to find that length, well, let's see that angle using the adjacent side and the hypotenuse side, because that's a right angle right there. I'm going to use cosine to say that cosine of theta is the height of my parallelepiped divided by the length of the vector w. Or in other words, the height is equal to the magnitude of w times cosine of the angle. But look, that's a formula you kind of might recognize. You've got the magnitude of a vector, right? Because u cross v is a vector, times the magnitude of another vector, times cosine of the angle between them. Oh, I should point out, sorry, I didn't say this, that the vector that points straight up is the direction the cross product points in. Because if you do u and you twirl your fingers towards v, you're pointing in the direction of the cross product, which is the cross product, up in this case. So that direction there, this is the direction of u cross v. So this angle theta here is actually genuinely the angle between the vector u cross v and the vector w. And if I want to calculate the magnitude of a vector times the magnitude of a vector times cosine of the angle between them, I should be taking the dot product of those two vectors. So this is really equal to the dot product of u cross v dotted with w. And then the absolute value of that, just to make sure it's positive and not negative. And I do mean absolute value here because u cross v dotted with w is not a vector, it is a number, scalar. You still might be asking, why do we care about this? And I would agree, it's kind of weird, but there is kind of a cool application. So, do I really want to do this? Yeah. So, yeah. Okay, so let's say we have the following. Let's say that, yeah. So we know that we have, yeah, this parallelepiped, which I don't really want to draw again. So let me just label these points here. So let's call this point A, this point B, this point over here C, and this point up here D. Then we can say that if A is equal to the point 1, 1, 1, B is equal to the point 2, 0, 3, C is equal to the point 4, 1, 7, and D is equal to the point 3, negative 1, negative 2. We could, if we really, really wanted to, use that to find the volume of the parallelepiped that those 4 points would give you if you found all like the right things. So I'm not saying very well. I apologize for that. So I have to find U, which is the vector AB, which is going to be 1, negative 1, 2. And I have to find V, which is the vector AC, which is going to be 3, 0, 6. And I have to find W, which is the vector AD, which is going to be 2, negative 2, negative 3. Right? Right, yeah. Okay. And then if you actually want to find the volume, first you have to find U cross V, and then whatever that's equal to, you're going to dot that with W. I really don't want to do this the long way because there's a shorter way of doing it. So here's what the long way would be. So U cross V, you would have to do I, J, K. I'm probably going to end up doing it, but you probably don't need to write this down. But you can if you want to, because, I'm not going to stop you. It's probably good practice. So let's go ahead and find U cross V. U cross V is going to be equal to, let's see, it's going to be I times. So I would encourage you to get somewhat good at this. I don't really want to write down I times the negative 1, 2, 0, 6 minus j times 1, 2, 3, 6 plus k times 1, negative 1, 3, 0. I really want to skip and say it's I times negative 6 minus 0 minus j times 6 minus 6 plus k times 0 minus negative 3. So I get negative 6i plus 3k. And then I'm going to take that vector and dot it with my w. So then u cross v dotted with w is going to be that vector, negative 6i plus 0j plus 3k, dotted with my w vector, which is 2i minus 2j minus 3k. And then it's going to be negative 6 times 2 plus 0 times whatever plus 3 times negative 3. That's going to be negative 21. That's why we have to make sure we take the absolute value of that whole thing and get positive 21. So the volume of a parallelepiped that has those coordinates as the three corners that are like adjacent, or the three corners that are immediately drawn from your initial corner. Or like I'm thinking of, sorry, I'm gonna cover this up for a second. As A being my initial corner, and B, C, and D are the corners that are like one length away from it. It's not anything that's like a diagonal away. That would have a volume of 21. Who cares? Okay. But here's the cool part. The cool part is you can skip all this and instead find your volume by doing the determinant of the 3x3 matrix, where instead of writing I, J, K, U, and V, you write U, V, and W, which I think is just kind of neat. So here's my U, here's my V, bless you, and here's my W. Where'd you go, W? 2, negative 2, 3. Negative 3, sorry. We're doing something cool. So this is where it's going to pay off that I talked about the fact that you can do the cofactor expansion along any row or any column. Instead of picking the first row, we'll do it both ways actually. So you could do it as 1 times 0, 6, negative 2, negative 3, minus minus 1 times 3, 6, 2, negative 3, plus 2 times 3, 0, 2, negative 2, which is going to end up being 1 times 0 minus negative 12, plus 1 times negative 9 minus 12. I'm a little worried here. Plus 2 times negative 6 minus 0. So I end up getting 12 minus 21. So I get negative 21, and then I still need the absolute value. However, I could have made a smarter choice, kind of. I could have picked the second row instead. It's going to be negative 3 times the absolute value of so cross out that, and you're going to do negative 1, 2, negative 2, negative 3, plus 0 times we don't care, minus 6 times, whatever that is, and then 1, negative 1, 2, negative 2. If we do it that way, we end up getting negative 3 times 3 minus minus 4. And then we get plus 0, and we get, I'm worried here, negative 6 times negative 2 minus negative 2. That's 0. That's negative 3 times 7, which is negative 21, the same result. And then we absolute value it and get 21. Cool. Kind of. So I do want this to be an important example to you that later on, when you take 22A and you're doing cofactor expansion to find the determinant of a matrix, you can pick any row or any column to do it along. And if you pick the row with the most zeros, it's usually less work. Okay, what is this useful for? One thing that I'm aware of. There's probably other things. Oh, sorry. Sometimes a little speedy over there. So one thing you can use this for is to answer the question, are these 4 points coplanar? Are the points 0, 0, 0, 2, 3, 1, 1, negative 1, 0, and 7, 3, 2, coplanar. If they weren't coplanar, then right, any three of them would be in like your base plane that was where the bottom of your parallelepiped sat, and the fourth one would be somehow above it, giving you the height of your volume thing. But if they are coplanar, that one sitting in the same plane means your parallelepiped has a volume of 0 because your height part isn't going to have any height. So we can answer the question, are these coplanar, by answering the question, what is the volume of their parallelepiped that they would generate? So essentially, we're going to think of this is our A, this is our B, this is our C, this is our D, and we're going to calculate U equal to AB, V equal to AC, W equal to AD. And really you can pick anything to be like your first point. I'm obviously picking A because it's 0, 0, 0, and it's easy to do. So my U is going to be the vector 2, 3, 1. My V is going to be the vector 1, negative 1, 0. And my W is going to be the vector 7, 3, 2. And then I'm just going to toss those into that formula and see what I get. So then the volume of the parallelepiped is going to be the determinant of, just throw these into my equation. So 2, 3, 1, 1, negative 1, 0, 7, 3, 2. And really, it doesn't matter which order you actually write them in. Like you can write any of them because you're going to take the absolute value at the end anyways. So let's see here. Picking the first row because it's convenient. 2 times negative 1, 0, 3, 2, minus 3 times 1, 0, 7, 2. In case you missed it when I said before, all I'm doing is I'm selecting 2, crossing out the row and column it's in, and then finding the determinant of the remaining 2 by 2 matrix. And then when I pick 3, crossing out its row and column, and I've got the remaining 2 by 2 matrix, 1, 0, 7, negative 2, and then covering up 1 and having that as my remaining matrix. So it's going to be plus 1 times the determinant of 1, negative 1, 7, 3. If we calculate this, we get 2 times negative 2 minus 0, minus 3 times 2 minus 0, plus 1 times 3 minus negative 7. And we end up getting negative 4 minus 6 plus 10, which is 0. So these points are coplanar because the volume of their really not parallelepiped would be 0. It's kind of neat. All right, where are we going next? Not there. Ah, yes, lines. Okay, so it's kind of a lot, I know. Let's talk about lines. So lines in 2 dimensions are easy, right? It's y equals mx plus b. You've kind of got a point, your y-intercept, and a direction, your slope. Well, in 3 dimensions, it's a little bit more weird, I guess, because you can't just say you have a slope because like if your slope is like, over 1, up 1, is it like this way or is it, which way are you pointing? Right? Are these lines parallel? No, one's going to like, so we have kind of other orientations of lines with each other than we had before. Yeah.
We have like 3 dimensions.
I kind of, but what we're going to do is we're going to say instead of having a point and a slope to define a line, we're going to have a point and a direction. And the direction is going to be given by a vector, which is one of the reasons we're talking about vectors. So let's write down some stuff. Equations of lines in 3-dimensional space. So we don't have nice equations. Instead, we write equations in parametric form. Now, parametric form is probably, well, it's definitely something that's in the syllabus for 21B. Sometimes it gets kind of cut off at the end. So it's where we write all of our coordinates, x, y, and z, as functions of a fourth parameter, usually t. So, for example, yeah,
Still like inter.
we're going to. Yeah.
So that's
No, that's not the thing you're asking about. It's a different thing. Although, yeah, okay. Anyway, so let's find, for example, let's find the equation of the line that goes through the points. Let's say 6 to -1 and 9, 7. Sure. -5. All right, so here's the idea. Here's my line. And here's the point P, 6, 2, 1, -1, sorry. And here's my point Q, 9, 7, -5. And here's what you want to imagine is happening. There's a particle traveling along this line. And at a constant speed. Let me actually probably write down the words I'm saying. Sometimes I'm bad at that. So imagine a particle traveling along this line at a constant speed. So let's say right here is when it's going to be at time equal to 0, it's at the point P. And then 1 unit of time later, it could be 1 second or whatever you want to think of. It doesn't really matter what the units are. It's over here at the point Q. So in that 1 unit of time, what happened to each coordinate? Well, it looked like, to me, the x coordinate has increased by 3. The y coordinate has increased by 5. And the z coordinate has decreased by 4. So we can say that the x coordinate gains 5. Sorry, gains 3, apologies. The y coordinate gains 5. And the z coordinate loses 4. So we can say that x as a function of time is going to equal 6 plus 3 times t. Because at time 0, x is 6, and 1 unit later, 6 plus 3 times 1 is going to give you 9. And then over here, at t equal to 2, we know that if t is 2, the x coordinate should be 6 plus 3 times 2, which is 12. The y coordinate is going to be the initial point 2 plus 5 times t. When t is 0, you get 2. When t is 1, you get 2 plus 5. When t is 2, you get 2 plus 10, which is also 12 by coincidence. And finally, the z coordinate is going to be the initial coordinate -1 minus 4 times t. When time is 0, z is -1. When time is 1, z is -5. And when time is 2, z is -1 minus 8, which is -9. And this is how we write the equation of our line L as parametric equations. 6 plus 3t, 2 plus 5t for y, and -1 minus 4t for z. Later on, when we start talking about vector functions, we'll just rewrite this as one vector, and we'll say that r of t is x of t, comma y of t, comma z of t. And so we'll describe the entire line as a vector function. I should say one more thing here. Technically, I should point out that the domain of t is all real numbers, right? Because you can go as far this way as you want or as far that way as you want. And that seems like a good ending place. We'll talk more about lines on Friday.